In this chapter, we're going to talk about, or this section, we're going to talk about infinite series, not sequences, but series. So, and then we're going to also discuss convergent or divergent series. But first of all, let's talk about what is an infinite series. Let's assume that this represents an infinite sequence. Then when we sum all of these terms, A1, A2, A3, An, and so forth, where n goes to infinity, then we call this an infinite series, or simply a series. Now, there's a series notation that you can use. It's a sum notation, so you can use this sigma, and this means you're going to sum all the terms of your sequence. So therefore, this would be a series when you have this sum notation here. Okay, and normally we're going to do this from n equal 1 to infinity, but you obviously can use this notation to where you go from n equal 1 to some other number. Okay, now I want you to consider this infinite sequence 1 over n, and now this, when I give you the sum notation, now here it tells you here that n goes from 1 to infinity. Now it's common that we'll go from 1 to infinity, but those limits do not have to be 1 and infinity. But if it's going to be an infinite sequence, then of course it does have to go to infinity on the top. Okay, so what does this mean? Well, this means that you take the term for when n equals 1, which would be 1 over 1, or 1, and then you add it to the term for n equal 2, which would be a half, and then you add it for the term for n equal 3, which would be a third, the next term, and then the next term is a fourth, and then so on and so on. And then, so you're going to have an nth term out here, but it goes on forever and ever and ever. So actually, that's what an infinite series is. It's when you're adding the terms of an infinite sequence. Now, this can be a little bit confusing, but the kth partial sum, which we'll call S of k, of an infinite series given by the sum of A sub n, is actually just the sum of the first k terms. So S of k would be A1 plus A2 plus A3 and so on until you get to the kth term. Now, we can actually talk about the sequence of partial sums that's associated with this infinite series. So let me show you what that actually means. But we would have S1 would be a term in the sequence, S2 would be a term, S3 would be a term, and so forth. So just to make sure you understand what we mean by this sequence of partial sums, so S1 would actually be just the first term. S2 would be the sum of the first two terms. S3 would be the sum of the first three terms, and so forth. And SK would be the sum of the first k terms. So that's what we mean. So if you put these together, you would have S1 would be A1, S2 would be A1 plus A2, S3 would be A1 plus A2 plus A3, and so forth. So, but it still would be a sequence, even though each of these S's represents a sum. Okay, so to illustrate this, let's consider we have the sequence A sub n equals n over n plus 1. Okay, so S1 would be the first term, which would be 1 over 2, because if n is 1, you get a half. S2 would be the first two terms. If n is 1, you'd get a half. If n is 2, you'd get 2/3. S3 would be the first three terms, so you'd have the half, the 2/3, and then if n is 3, you'd get 3/4. And then you'll notice I went ahead and added these up. So the first for S1 is a half, S2 is 7/6, S3 is 23/12, and so on. So if you wanted S4, then you would add up the first four terms. So that'd be a half plus 2/3 plus 3/4 plus 4/5. which is turns out to be 163 over 60. So the kth partial sum would just be 1/2 plus 2/3 plus 3/4 plus 4/5, etc., plus k over k plus 1. Okay, so now the sequence of partial sums would be the half, comma, the half plus 2/3, comma, the half plus 2/3 plus 3/4, comma, the half plus 2/3 plus 3/4 plus 4/5, comma, and so on. Or if you wanted to write the actual values out, 1/2, 7/6, 23/12, 163 over 60, and so forth. So this is just to kind of show you what these partial sums are. So there's really no objective here other than to show you what a kth partial sum is. Here's another example. So let's say that the sequence is 0.1 to the n. Well, then the first partial sum would be 0.1 to the first. The second partial sum would be 0.1 to the first plus 0.1 to the second. The third partial sum would be 0.1 to the first, 0.1 to the second, 0.1 to the third, and so forth. And so, you know, the kth partial sum would be the 0.1 plus 0.01. Let's see, do I have that right? Yeah, it would be 0.1. Yeah, it would be the first term, which would be 0.1, then the second term would be 0.01, then the third term would be 0.01, and so forth, out to 0.1 to the kth power. So that would be the kth partial sum. And then the sequence of partial sums associated with this would be 0.1, comma, 0.11, comma, 0.111, and so on. Okay, so we've got a convergence definition here. It says an infinite series here, a sub n, and remember with the sum there it means series, is convergent if its sequence of partial sums s of n converges. That is, if the limit of s of n as n goes to infinity, where s of n is a sequence, if that equals some number s. So if this sequence converges, then the infinite series converges. So remember, the limit s is actually the sum of the series, and we write s as a1 plus a2 plus an, and so forth. So this series is divergent if the sequence of the partial sums diverges. Okay, and a divergent infinite series actually has no sum. So let's prove that this series that starts 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4, etc., which would be 1 over n times n plus 1, converges. And we'll prove that it converges, and we'll see if we can find its sum. Now this is kind of a weird guy here, so let me just show you how we do this. One trick we're going to do is we're going to break up this using our partial fraction that we learned about earlier, and we can actually rewrite this fraction as 1 over n minus 1 over n plus 1. Well, then the partial sums would look like this. So if n is 1, we'd have 1 minus a half, and then if n is 2, we'd have 1/2 minus a third. And then if n is 3, we'd have 1/3 minus a fourth. All the way out to if n is n, we'd have 1 over n minus 1 over n plus 1. Now if you'll notice here, all the terms cancel. Minus a half plus a half cancels, minus a third plus a third cancels, minus a fourth plus a fourth will cancel, so forth. Minus 1 over n cancels with plus 1 over n. So the only two terms I'll have left is the 1 and the minus 1 over n plus 1. So this sum actually is nothing more than 1 minus 1 over n plus 1. And another way to write that is n over n plus 1 if you got a common denominator. So n over n plus 1. Now, if you take the limit of this sum as n goes to infinity, then you actually get 1. So the series converges and has a sum of 1. Okay? Alright, now this series has a special name, so remember this series. This is actually called the telescoping series, and when I write this, if I don't write anything here, you just assume it goes from n equal 1 to infinity. So this is the telescoping series, and it will be used out through this chapter. Okay, this one's going to be a weird duck too, but we're going to prove that the series 1 over n diverges. In other words, 1 plus a half plus a third, so forth, plus 1 over n diverges. Okay, so here we go. So let's write out some terms. So it's going to be 1 plus a half plus a third plus a fourth plus a fifth through 1/8 plus 1/9 through 1/16 plus 1/17 through 1/32. Okay, well, you can show that the sum of the first two terms, S2, is 1 plus a half, which is greater than 2 1/2. And then you can show that the first four terms, these four terms here, are actually going to be greater than 3 times a half. And then you can show that the sum of the first 8 terms is actually greater than 4 times a half. Okay? And then if you continued, you could show that the first 16 terms is greater than 5 times a half, and the first 32 terms, the sum is greater than 6 times a half. And so through mathematical induction, we basically can show that if you have the sum where we're taking the 2kth partial sum, that's always going to be greater than some number. Okay? Well, since that's always going to be greater than some number, then this sum goes to infinity. Then the sum of the series, the sum of the partials, the limit of the partial sum as n goes to infinity is infinity. Well, since the partial series here, since the series of the partial sums diverges, then the infinite series must diverge. And this series has a name too, and it's called the harmonic series. So remember that the harmonic series diverges. So that'll come in helpful later. Alright, now I'm going to do one more, and then we're going to shut this video down. Show that the series -1 to the n minus 1 diverges. Well, I've already shown you this once, so the series actually it actually diverges, because here's what's going to happen. If you take the first two terms, well, if you take the first term, you get 1. If you take the first two terms, you get 0. If you take the first 3 terms, you get 1. If you take the first 4 terms, you get 0. If you take the first 5 terms, you get 1, and so forth. So the partial sums actually oscillates. The sequence of partial sums actually oscillates between 1 and 0. So therefore, the limit of the partial sums as n goes to infinity does not exist. Therefore, the infinite series must diverge. Okay? So I'm going to take a break from right here, and then we're going to pick up with the geometric series on the next video.